Much, Pierre. Thank you very much for your presentation. And let me thank the organizers for a very kind invitation. I do apologize. I was not able to come, and I actually do regret that, but it was too difficult. So I've chosen a topic for today, which is very basic. So maybe it will be even too simple to some extent, and is motivated by things which I was interested in mean-field game theory, but it is also independently, an independent topic. So I will probably not go too much into mean-field game issues. So I will start from that anyway. So the motivation for what I want to discuss with you today was, this issue of the long-time convergence of mean-field games. This is something in particular, one of the main collaborations that I had with Pierre. And just to mention, so where this kind of interest comes from, when you look at the long-time behavior of mean-field game system, so this is the simplest case, and it is in the monotone case, or eventually mildly anti-monotone, as we made a bit more clear in the paper with Marco Cirant. What you would expect in a stable situation is that the solution, which is a solution of the system in zero capital T, then it behaves like stationary for most of the time. And you may quantify this in this kind of estimate, which I was also maybe mentioning a few days ago. And to obtain this kind of, say, pointwise estimate, you need an interplay of the stability properties of the two equations, say Fokker-Planck and Hamilton-Jacobi. So I will just briefly recall where you use this interplay. So first of all, of course, there is the monotonicity. So this kind of arguments rely on two basic ingredients. So one is the monotonicity, and this is specific to mean-field games, and the other is somehow even independent and are robust decay estimates of the operators involved. So to understand that, you should, for example, take the difference between evolutionary and stationary state and just look at sort of linearization, if you want, which is so the equation of the difference. And where the monotonicity comes into play is that if you use also the convexity of the Hamiltonian, there is a functional, which is essentially the scalar product of mu and v, as in the optimal control viewpoint. And this is strictly decreasing in time. And actually, the quantification of the rate of decreasing is given by the lower bound of the Hamiltonian and then the gradient square, which means in particular that this quantity here, so the integral of dv square against, say, the invariant measure, is bounded, can be estimated by, say, the scalar product, and in particular by an estimate of mu and v into nice, say, good working duality spaces. If you want to take out something from this kind of decreasing inequality, then you should somehow try to close the estimate. And to this purpose, it is here that you need to understand the decay estimates and the global estimates in time of this kind of equations. And that's the spirit of, that's the content of my talk. So, for example, a global in time estimate would be that the measure mu of t is estimated with a constant which is independent of the horizon, is estimated in terms of, say, the L2 norm here of this field. And as far as v is concerned, for example, a backward decay of v in terms of its right-hand side, which would be this kind of operator, And then, of course, if you might use the line above to enchain this with the estimate of mu. And you see, this would allow to close this estimate here in terms of the left-hand side and so on. So that's a sort of toolbox that we understood in particular in my paper with Pierre on the long-time behavior of the master equation. And so it is in this toolbox that I want to discuss. So this robust decay estimates. So in particular, here you have a Fokker-Planck equation, and you have a decay of mu. And a point which is important, when I say robust, it means that you would like to have some estimate whenever you don't have very precise information on the drift. Okay, so, or at least maybe I cannot say, of course, that you have a partial information, which would be much stronger, but I would say that you don't know this drift maybe very, very well, because it comes from the adjoint problem. Okay, so even the estimate that I was mentioning before, this is, okay, you take the solution mu of this equation, and then you would like to have a global in time estimate. In general, the second estimate, so this one, is in general obtained from the first one plus Duhamel's formula if you have a nice decay. And then, okay,
Alessio, excuse me to interrupt you. This is Pierre. Just to be sure, here you assume that L is uniformly elliptic, right?
Okay, okay, so that's the point. Okay, so I didn't say anything so far because I wanted just to underline a bit the toolbox, which is more or less needed in the, for example, in this business of combining the two equations in a Milfield game system. So now, this is well understood so far for, say, Brownian motion or uniform diffusion, and also when the state space is compact, which, say, for example, on the flat torus. So the point in my talk is to discuss this kind of estimates in a more general, say, situation. So the key word in my talk is time decay rates for, say, Hamilton-Jacobi and Fokker-Planck, in a situation which is, for example, a non-compact state space for X, but some compactness induced by confining drift. So that's the typical situation of Horst and Uhlenbeck operators. But in particular, I would like to stress the case that L can include jump processes and typically Levy processes. So the case, the prototype here you should think about is a fractional Laplacian, okay? So this is one of the main points, is to try to go a little bit beyond the case of, say, Brownian diffusion, okay? So when you attack this kind of a question, well, there is a very extensive literature, so that's a very classical problem on the rate of convergence of a Fokker-Planck equation with local or non-local, say, operator L towards a stationary measure. And this is, as we may guess, or as we may know already, this is related to the ergodicity of the associated or stochastic process behind, because, well, simply if you have this kind of convergence of a solution of a Fokker-Planck equation towards some measure M bar, in particular, well, this reflects the fact that the time average of, say, observations along the trajectory will be described, and the limit will converge to the space average in terms of the invariant measure. So, of course, there is a relation between ergodicity of the process and convergence of the Fokker-Planck equation. And I repeat, the prototype, and this is why you need some kind of help from the drift in this case, because if you think to pure diffusive situation where you somehow you need to restore ergodicity somehow, so you may be in a non-compact state space, but your drift should help somehow to get this kind of ergodicity. And that's why the typical example here is the Fokker-Planck equation with confining drift. Okay, so first of all, I will rephrase this problem for decay at zero of zero average solutions. Well, of course, in the linear case, when B is time independent, this is totally equivalent, but I prefer this kind of formulation for obvious reasons. So first of all, I can discuss the issue of decay at zero for time-dependent drift here. And also, this is exactly what you need when you linearize in Milfil game situation, for example. So I would rather rephrase the problem of convergence to equilibrium in a problem of time decay of zero average distributions. Okay, so of course, this started, I must say this is quite a recent work, and it started, as you may guess, exactly because I was involved in answering this kind of question for Milfil games. And then I started also look what was known in the literature. So there are two typical results here. One is when the drift is strongly confining at infinity. So that's exactly the rate of the Orchten-Uhlenbeck. And in this case, in some space X, you have exponential decay of M. Contrast, if you have a still confining drift, but with, say, less strong, say, force at infinity. So here you have this is called in the literature the slowly confining drift. Then you get a subgeometrical rate of convergence, meaning that you get something which is not exponential. It might be polynomial, or there might also be maybe things in between. But okay, so the space which is typically involved in this kind of estimate, naturally involved, is in L1 space with weight. And to put things, simple, in particular, we'll often use weights which are essentially powers of X. And so rather than using the absolute value, so let me use the square root of 1 plus X squared. And so this involves essentially moments. So you see, this is a typical space where you get that is for L1 with some, say, X to the K in weight. And this gives a stronger convergence of M rather than just the L1 norm. But it requires a bit more, some moment finite for M0. So let me give a very partial, I would say, look at very huge literature. But it was very instructive for me to try to understand how people in general prove this kind of things. And there are two major, I would say, approaches. One is more common and inspired from the case that the drift comes as the gradient of a potential. This is in particular, one of the first results was just using, just linear spectral gap theory in L2 of some weight, in this case of the exponential V. And this was a result by Gross in 75, and then initiated a long series of results in this direction. And many results in the semigroup theory were obtained with this spirit of using self-adjointness in a weighted space. But then I would like to say that in my viewpoint, that this kind of approach evolved crucially since the works by Toscani and Villani, in particular, in entropy dissipation methods, which consist in showing that a certain quantity, which is, as they explained, sometimes it's more naturally the entropy related to the solution rather than a weighted L2, say, norm. And so a decreasing, say, character of the entropy is a relative entropy. So you see it's a relative entropy with respect to e to the minus v in this framework. And this provides with decay, and in particular exponential decay or even sub-exponential decay. And there is a very popular fields of research. For example, Markovic, and in particular, I would say Carrillo, in many different also contexts, use this kind of idea. So this approach relies on functional inequalities, starting from the logarithmic Sobolev inequality. And there are also extensions to non-local cases, but I must say that the extension to non-local operators starts being a bit awkward in this kind of approach, because it's not easy to export this kind of structure inequalities to a general non-local situation. So there are partial results, but it is they are not, I mean, as complete as what you may get with a second, say, field of approach. So this is probably well known to many people, I would say, in the audience, because this is the approach that probabilists use to establish this kind of results. And so the typical setting is just to look at M as the, say, the semigroup solution generated by some diffusion process. And two properties are crucial here in order to establish the exponential convergence. So I presenting that here in a PD viewpoint, but of course they were essentially introduced in a probabilistic approach by Mine and Tweedy. Even this is, I mean, goes back to the idea of Harris recurrence theorem. I would say that I really liked and was strongly inspired by the revisitation that Martin Iron and Mattingly wrote on that in 2011. So this was very instructive to my comprehension, I must say. But in terms of PDE, their approach could be stated like that. So there are two ingredients. One is the existence of a Lyapunov function outside a compact set. This is why this approach is often called the Lyapunov function approach, which means the existence of a function phi. Okay, typically a function phi is going to infinity at infinity, so it's a typical Lyapunov function, but this is just a strict super solution outside a compact set. And then you also join that with a property of strict positivity preservation, that M is strictly positive uniformly in compact subsets, and then you get this exponential decay. And typically the L1 weighted space here depends on the Lyapunov function. An important article, over 100 of citations by Bakri, Catio, and Guillen in 2008 that makes a bridge actually between the different approaches using, say, Poincaré or inequalities or Lyapunov functionals. And many developments later, in particular, there is a whole set of papers by Michler that developed this idea in combination with the composition methods of operators and things which are maybe even more general, but somehow also a bit more complicated to my viewpoint. And also there are extensions to non-local operators. In particular, there were recent extensions to non-local operators by Lafleche, and this was also another paper where I started from to understand things. Okay, so let me conclude more or less this comment on the existing literature. Well, I would say that the approach with functional inequalities is very elegant, and it has this connection also with the hypocoercivity notion developed by Villani, and also has the advantage that it gives sharp rates, but of course in explicit examples. But the drawback is that it requires, to my viewpoint, say, knowledge on the stationary state, which is also difficult to get in when you are in coupled systems, and also is difficult to adapt to general diffusion processes. And the approach via Lyapunov function is definitely more general, and what I present is maybe an analytical also viewpoint, new maybe revisitation of that. Okay, the only drawback that I found in the literature, and that's why I decided to suggest maybe a new kind of approach, is that what I found was not really user-friendly. So you have a coupled system, so you need this kind of result. So you look in the literature, and very often you have to verify properties of the semigroup. You don't even know if you can define a semigroup because your drift is time-dependent. So, okay, of course you can reprove that at hand, but okay, so somehow I was not satisfied for two reasons. One was that I was needing this kind of result for time-dependent drift, which was very rarely the case in the literature. And the other is that many of them required assumptions on the divergence of the drift. And was not ready to accept that, because in the Mifflin situation, this drift B is the derivative of the Hamiltonian on the gradient of view, and its divergence involves second order derivatives, and I didn't want to use informations on that. So this is more or less the reason why I came just to suggesting maybe a slightly different approach, which I think can be of interest, and that's why I'm discussing that with you today. So the sort of simplification of some of these ideas that I want to convey is based on two essential points. So one point is that by duality, my first point is that the decay of Fokker-Planck equation can be entirely deduced from essentially ergodicity type or dissipation estimates of drift diffusion equations. And that's the first, say, point. And so if you go back a bit on this approach, which is called sometimes the Mine and Tweedy, or which was popularized also in those papers by Eirer. So you see that those properties are, of course, in probabilistic terms, you understand that these are related to properties of the process behind. But in terms of PD, there is some property that you need to prove on the Fokker-Planck equation, which is sort of Arnack inequality, and other properties that you would like to check on the adjoint problem. And okay, so I found it simpler somehow to say, okay, let me clarify, first of all, the results for the Fokker-Planck equation can be entirely deduced from estimates on the drift diffusion equation. And those estimates involve a semi-norm of view. So of course you cannot expect when you have this kind of ergodic situation that you estimate on a norm of view. So they must be estimates on a semi-norm of view. And so this is why I'm going to use this weighted oscillation of view. Typically phi of x will be a Lyapunov function. And so in my notation here and later, this bracket of view phi just means the oscillation of view weighted by dividing by this Lyapunov function. And in particular, if you find this bracket with x to the k, it's just the oscillation of view divided powers of x and y to the k. What is the sample result I am say trying to sell you? The sample, okay, I've written that just for the prototype, just to make it simpler, the statement, and to understand the kind of assumptions. So imagine you have, say, a fractional Laplacian plus a drift term. Okay, so you have two conditions on the drift. So one is the confining condition at infinity. So this is the case for the strong confinement condition. And then you have another condition which involves a little bit of, say, regularity of B. I will maybe comment that in a minute, but okay, this is depending whether you have a bit more of diffusion or a bit less of diffusion in your operator, okay? So under these conditions, then you get an exponential decay of this semi-norm of view in terms of U0. Okay, nice. Then theorem B, under the same conditions, you take the solution of the Fokker-Planck equation.
Alessio, may I ask a question?
Yeah, sure.
Just on this slide, there's in the red line, on the right-hand side, there's no square on the x minus y?
There's no square. There's no square. Okay, so
and just can you precise the regularity you need on B?
Yes, I will precise it in a minute. Okay, so I first just wanted to state that under the same conditions, well, it is maybe evident for the good students that, but okay, for me it was at the beginning not entirely evident, but I will also say in a minute a word that theorem B can be indeed by duality deduced from theorem A, and then you get the exponential decay in L1 of this, say, weight, simply say applying theorem A plus one page of slides that I will show you in a minute. Okay, so what are the assumptions on B? Okay, so of course, one is the confining. So if you look at this condition, so first of all, you think that alpha, you have a bit of diffusion. Okay, so alpha is bigger than 1. Well, essentially, this says that on bounded range of interaction between x and y, B just needs to be bounded. Okay, so that's nothing more. Of course, when you have long interaction, it includes a bit of dissipativity, and this is why this is a one-sided condition. Okay, so I would just say that essentially in what I call the elliptic case, which means alpha bigger than 1, you need for B confining at infinity plus, say, locally bounded. Of course, it is not exactly like that, but in my mind, this is a bit of dissipation in some direction at infinity. And like of course, if you write here the Jacobian of B, you can visualize a bit more that there is one part which is penalized. It's a one-sided condition, but locally, when x minus y, so that's probably the question by Dan, you see that locally you don't need very much. And when you get at a case with less diffusivity, okay, you just improve locally, you improve a little bit with some Hilbert regularity. This compensates for a bit of lack of diffusivity in the operator. But to my viewpoint, those are very transparent conditions. So you don't need to prove any property of the semigroup. You just take, and any perturbation result, you already have perturbation result inside B in this condition. Okay, so you don't need to prove too much. That's my viewpoint, but okay, I may be wrong. Okay, so as I said, some local Hilbert regularity is required on the drift for the less diffusive case. Okay, well, the proof of theorem B from theorem A, as I said, was just duality, which means that, of course, you evaluate the solution of the Fokker-Planck equation on the backward solution given by U in this case. So you will realize it's not by chance that they are called the U and M, of course, here. So they are, of course, reminiscent of my notation in Mifflin. And then you observe that, okay, M0 has 0 average. So you may add any constant here to U of 0, and which means that then you use the duality with M0 in L1 weighted and the U0 plus C in L infinity of, say, the dual situation. And there is just one remark. So this is the remark is that if you take the infimum over constants of this, say, family of norm, that's exactly the semi-norm in the double variables that I mentioned before. So that's maybe the only step which, okay, I needed also to realize, just if you wanted to understand that the behavior of the Fokker-Planck could be entirely relying on this weighted semi-norm. And then, of course, once you minimize then on C this inequality 1, then you get that the evaluation of M is now estimated simply with the semi-norm of U at 0 by taking the nth over all constants. And then you get this you use the exponential decay of the backward equation, and then you are done. So I would say this is very pedagogical, even, I mean, in a course, if you want to explain this kind of things. Of course, it's a PD perspective. I totally am aware of that. And okay, so the advantage of this method is that if you look at a slowly confining case, then you don't have to invent anything different. So it's not like you get from strong Poincare inequality to weak Poincare inequality and whatsoever. So essentially you do the same, and you just will get polynomial decay for the oscillation of U, and then you deduce polynomial decay for the oscillation for the Fokker-Planck equation. So there is just one technical point here, is that this polynomial decay is not for free, and it actually depends on the fact that you are measuring M with some moment K at the expense of a slightly stronger moment on M0. And the gap between the two is exactly the polynomial decay. Okay, so when I looked at this kind of, when you look at the proof, you realize that quantitatively you cannot really do better than that in the proof. But then, okay, I looked in the literature and all previous results were of this type. So, I mean, I just got, so far, I understood that this is probably inherent, the difficulty of going in a subgeometrical rate. Okay, so let me now also say why I think this kind of approach might be interesting, independently of the fact that it is maybe slightly more general in some direction or whatever. I think that the interest is in the estimate that you prove for this drift diffusion equation. So this is, of course, not revolutionary, but it's much simpler in my viewpoint than what I saw before. So the point is that you get, so now I'm going back to the crucial point. Okay, so you have this drift diffusion equation and you want to estimate the oscillation of u and to get this exponential decay. If you rephrase, so if you write this semi-norm, that's exactly saying that u of tx minus u of ty is dominated by this. If you look at this kind of estimate, at the beginning, you're a little bit puzzled because, okay, you think, oh, okay, well, this is a sort of Lyapunov functional. Sorry, is a sort of Lyapunov function. So you expect it to be a super solution. So, but actually this is not a strict super solution everywhere. And this is the only, I would say, idea that it's much better to prove a different inequality, which is stronger in the sense that it implies 3, but to some extent, it's more natural. So I immediately thought that this inequality is more natural, even if apparently it is just, stronger than 3. So what is now the function psi? So I just claim that it's enough for me if I prove that for some bounded function psi. And of course, if psi is bounded, then it is dominated by this Lyapunov functional. So 4 implies 3, but 4 is much more natural. Why? Because somehow it's different. You cannot prove that this is a strict super solution. So you need some help when the interaction between x and y is small. And that's the idea of this approach, is that, okay, the function psi will take care of the small range interaction. So typically psi will be a concave bounded function. Actually, I would say locally Lipschitz or locally Hilder. And the long range interactions in x and y, those are ruled out by the Lyapunov function. I will say it a little bit more precisely now. So this is the kind of estimate. So that the only, I would say, new estimate is, okay, let me prove now this kind of estimate. U of x minus u of y is smaller than the sum of these two contributions. One, I call it the Lyapunov function contribution, and the other is, I call it sort of local ellipticity. Okay, so this estimate is an evidence of an ergodic, of course, phenomena of the process. And indeed, this is not new in itself. And there are those kind of estimates. There are plenty of similar estimates in the probabilistic literature. And they take the form of say, contraction estimates in some Wasserstein metric for the transition probabilities associated to the semigroup. So, I mean, I could quote many people, but just those that, I mean, I have looked at a little bit more closely. Of course, there are many works by Fangio Wang, then by Eberl and Schilling Wang and Micah also quite recently. So I understand this. Of course, I am on one hand I am presenting that to, of course, an audience where there are huge, experts in probability, but at the same time, of course, one of my goals was to give an entirely analytic proof of this kind of estimates. And I would say even quite elementary. So everything is just based on maximum principle and of course on the doubling variables method. So this is a revisitation, if you want, of doubling variable methods of viscosity solutions. And I should mention that actually this kind of use of doubling variables for regularity dates back mostly to the papers by Ishii and Lyons in '92. And this was also extended to non-local operators in papers by Barr and collaborators, and in particular by Barr, Chassain, Chomaga, and Cyril Humbert. But to be honest, this was not enough in this business to get this kind of estimate. So you need also new ingredients, even if you want to go through the doubling variables. And the new ingredients, that's maybe the interesting part for me. So the new ingredients come from the fact that you should embed, that's my viewpoint, the idea of the coupling methods that probabilists use into the analytical doubling variable method. And to be honest, this is something we addressed, me and Enrico Priola addressed that already in 2012, then when we showed that there was an equivalence between the approach that was used in probability with coupling methods and the approach which was used by analysts in viscosity solutions. There was a sort of equivalence, at least for, we showed that for local diffusions. And so let me spend maybe some words on that. And of course, I need to say something which is maybe largely well known to a big part of the audience, which is what do we call coupling method in probability. I might, of course, maybe miss many references, but at least some basic references go through the idea of doubling at the beginning. And in particular, I learned that from Limbaugh and Rogers, and then Chen and Lee in the 80s. And more recently, they were used also in much more general context. So there is a whole, say, set of, that's a whole direction of research in probability to use coupling methods. What do we mean by a coupling? So a coupling, to some extent, you may just imagine that's just you take the probability distribution associated to a process, and then you just look for a coupling of the two probability measures. That's exactly, but in terms of stochastic processes, you can present it like that. So you are given a process starting from point X and another process starting from Y in RT, and then you look for a new process in the product space such that the marginal laws of Z are the laws of XT and YT respectively. And this is precisely, this is what probabilists call the successful coupling, meaning that once you hit the diagonal, then you remain on the diagonal. So somehow that's this process ZT after the first hitting time of the diagonal when X is equals to Y in the product space, they just follow one of the two paths. Okay, and where is this used in and where is that I learned, I mean, this kind of methods in probability? And I hope that to Enrico Priola, who taught me that, was that, okay, when you want to estimate the Lipschitz character of the solution of the PDE, then of course you can represent, at least in the linear case, that's what he presented to me at that time, you represent U as the expectation along the process XT, and the U of Y is the expectation with respect to the same kind of process, but starting from Y. Okay, so let me call it YT. But then, of course, this expectation is the same for any coupling that you may build of the two processes. And in particular, you can estimate that only for the time which is smaller than the heating time, at least for a successful couple, for the couplings as I define. And in particular, you can say, okay, this is roughly smaller than 2 times the L infinity norm of U0 times the probability that T was smaller than the heating time. So the Lipschitz estimate for solutions are reduced to estimate the heating time of the diagonal best over all couplings. And this is where probabilists started to elaborate and to work on what is the best way of coupling, say, diffusion processes in a way to optimize this kind of estimates. And in particular, one of the celebrated ideas by Linville and Rogers was to exploit the coupling just by reflection of, for example, for a Brownian motion, just to exploit what happens, and in particular, the optimization that is indeed achieved when you double a Brownian motion just by reflecting it through, of course, this is the orthogonal hyperplane to x minus y. With Enrico Priola in 2012, we explained that there was an immediate, say, counterpart in the analytical version that explained why the results in viscosity solutions were absolutely parallel to the results obtained in the probabilistic community. But at that time, at least, but I think even now, those communities were not cross-citing themselves, even if the results were more or less exactly the same in the end. So in the analytical version, you would say that if U and V are a sub and super solution, then you take the difference, U of x and minus V of y, and this is actually a sub-solution for a whole family of operators in the product space, where you build a new matrix of diffusion, but you have the freedom to choose this coupling, this mixed type diffusion C of x, y. So that's the coupling term. Of course, you have some constraints, and this is the constraint that the matrix is still elliptic. And then roughly speaking, you can say that U of x minus U of y is smaller than all the possible super solutions in two variables for all possible, say, diffusion, linear in this case, operators in the double space. And typical example, you take the identity, you take the Brownian motion, and then psi, you take a radial function of x minus y, and it turns out that the best choice here is exactly obtained when C is the reflection operator, as the probabilists were also using at that time. But the fact is that what I described here is purely nonlinear in PD terms, because essentially this is a result in viscosity solutions. That's exactly what you do when you double variables in viscosity solution theory. You show that U of x minus V of y is a subsolution of an operator in the double space. So the coupling methods are essentially already embedded into the doubling variable approach. Let me just give you an idea of what I can do for jump processes. So roughly speaking, what you want, back to my estimate, so I would like to show that U of x minus, I would like to show that this function W is negative, okay? So that's the estimate I was aiming at. And so so the claim is that no positive maximum can occur. And then, okay, suppose you have a maximum, that's a typical argument. If you have a maximum, then you can, of course, compare this maximum value of W with different kind of, say, jumps, if you want, of x and y, if you want to call that way, or different kind of movement from x and y. So if you just take, for example, if you just say that the maximum point W of x, y is bigger than W of x plus z and y plus z, well, you just get that your, say, Levy operator, L of U of x minus L of U of y, is just bigger than the operator computed at this function phi of x. Why? Because you see, if you take x plus z and y plus z, the distance between these 2 points is exactly the same as x and y. So this term here of psi would cancel, so it would go away. But you can do much better. And in particular, you can use this idea of reflection at that stage, at this stage here, precisely here, you can insert the idea of the coupling. So that's what I was referring to, insert the idea of coupling here. So for example, you can say, yes, but my maximum point is also bigger than the evaluation when x makes a jump at z, but y makes a jump A of Z. And this A, for example, I can take the reflection of the jump. So if you do that, just simply you insert this idea, you prove this crucial lemma, which is crucial in the estimate I was saying to you, which is that you take a Levy type operator like that, assume, so this is assumed by now that this Levy measure is dominating, for example, the kernel of the fractional Laplacian. Then if you do have a local maximum point of this function, then you get an estimate, you see, for L of u of x minus L of u of y. And now this estimate includes the part for the Lyapunov function and a part which with a minus, it's like minus, okay, Laplacian, but it's non-local, of course. And it's like the second derivative of psi. So it's like minus second derivative of psi, but with a bit of non-locality here. And this is the crucial lemma. And from that, you may prove all the estimates that I was telling. So there is nothing more than doubling variables, maximum principle, if you want, behind. And this idea of inserting this idea of coupling in this argument. Okay, so I'm arriving quickly at a conclusion. So I just want to mention that similar arguments also apply to get regularizing effects in particular. Okay, this is of course an example when the diffusion is if it is alpha Laplacian, it must alpha, sorry, it is alpha half Laplacian, it must be alpha bigger than 1. So you get a kind of also estimate for the gradient, but this does not cost much more. And okay, I just presented to you, of course, when you have Levy measures which are dominating sort of fractional Laplacian, then it's reasonable, this is homogeneous. So you see here, this is homogeneous, and then it's reasonable to choose just the reflection coupling. But different choices will provide extension to inhomogeneous fractional diffusion. So it's now once you understand the strategy. And so I repeat, this is the key idea as I already tried to convey, so that the doubling variables, which is a nonlinear method, I insist on that, allow to embed these coupling ideas into its version. And then there are things which are less, there are extensions which are by far less obvious, and this is a more tricky perspective, but I am totally convinced that there is something to understand there, which is to export similar approaches for operators with more complex settings. So for example, for degenerate operators where this ellipticity is more hidden, it comes from maybe Ormander types of diffusions or maybe kinetic models and so far. But this is something, okay, it's maybe just part of this project that I somehow started because it's quite recent. Okay, I'm skipping essentially the application to Memphis game. So I just want to conclude. The conclusion is that, okay, I'm suggesting essentially a new strategy, which is just an upgrade if you want, or an update of things also we were in the air. The crucial point of this strategy is on the estimates of the weighted semi-norms. So this is maybe the key point on the weighted semi-norms of the adjoint problem. It's nice that you can recover actually many results obtained with many different methods and also sometimes in a quite complicated settings. And they are more or less here approached with the same strategy. From the probabilistic viewpoint, I cannot say that this is substantially different. It's probably just an analytic version of this powerful approach, which also I learned through some of these papers, in particular from the paper by Hyrer and Mattingly. But it still contains probably the analytical version of this coupling methods, which, okay, I already tried to popularize in 2012, but still few analysts are maybe using that. And okay, in terms of Memphis games, this is a work in progress with Espen Jacobsen, who actually came with this kind of problem at the beginning. And so we have, of course, used now these estimates in getting this long time behavior of Memphis games with Levy operators. So far, we discussed the simple situation where the diffusion is fractional Laplacian bigger than 1/2. So that's a little bit more diffusive. But we are also discussing now other cases, and okay, so we will go on trying to use now this kind of estimates as far as possible in this setting. Okay, so I thank you for your attention, and I leave some space for remarks if you do have.
Thank you, Alessio, for the nice talk. Are there questions in the audience?
Thank you, Alessio. This is Dan here. Very fascinating analogy I hadn't seen before here. I'm wondering if you can elaborate just a little bit, maybe go back to the slides where you introduce the Z, the coupling basically, or doubling of variables for the analysts here.
Yeah, I mean, okay, so
how should I think about the Z? Is this new operator AC, is this corresponding to a coupling of the two SDEs that U and V correspond to?
Yes, essentially, yes.
But it seems like you would need some...
Yeah, essentially here you can look at that. Of course, I mean you are preserving here. So there is a constraint. You are preserving ellipticity for this matrix. Somehow, I mean this can be associated diffusion process behind. Yeah, sure.
You would need some conditions on C in order to know that the marginals were U and V, right?
Yes. Well, I mean, yeah, the marginal are here. So you see, I use the same Q of X here and the same Q of Y. So you see that I'm just moving the mixed terms in my diffusion.
Oh, I see. You're basically correlating the Brownian motions with the C of XY. Okay. Thank you.
This is just the easiest case. I mean.
Okay, thanks. I wanted to understand this point.
Other questions in the audience? Charles, Charles, go ahead.
Yeah. Okay. Thanks for the talk, Alessio. I had a question, like a bit technical question, because usually for viscosity solutions with jump operators, somehow you can cut the integral part near the singularity and away, and somehow usually this sort of coupling kind of disappear. Like you do not need as strong couplings such as in the purely diffusive case, and here it seems that you really need this. Can you explain why? Like, is it because you need something more precise?
Yeah, I mean, okay, so here you have, I mean, your Levier type operator. And of course, I mean, somehow, as you say, when you do the doubling variable here, you can cut the local part. But in this, to this extent, you are also somehow neglecting the ellipticity of the operator.
Yeah, I agree, but it's like in the first paper on this, if I'm right, like the paper of Awatif and Barlenheimer and Arizawa, it's what they do. Like they treat it almost as a first order PDE. But
yes, but
you say that doing this you get more precise information, right?
Well, of course. I mean, of course, you can treat a second order or even a fractional, say, order more than one, like first order. This is the generate ellipticity if you want. So you can treat it as if it is just totally degenerate, but you are missing something. And that's what, of course, you need here, because this kind of estimates, they, as I tried to explain, they come by exploiting the ellipticity, even if it is mild ellipticity, it's a fractional type of ellipticity. Well, you need to exploit that because those kind of ergodic type estimates, and it is intrinsic also in the method, they need to exploit the ellipticity. So you somehow here, the point is how to use that to the most useful possible way. So, and this is why I had somehow to revisit also a bit what Barl and others, and Imbert and others were doing, even if they were already, I must say, they were already using also this kind of arguments for getting some local Hölder or Lipschitz estimates. But in this kind of business, when you want to get the rate of convergence in a long time, you need to be somehow more careful not to waste anything. And so this is more or less where I realized. And so my point, I mean, in technical terms, if you want, is that you can have smarter somehow ideas, exactly as you see in this page. When you want to analyze the maximum points of this W, you can use, say, some comparison which more or less stand on this idea of coupling, and this is giving a little bit of, I would say, advantage, and you gain something compared even to the other papers that you have in mind on viscosity solutions.
Okay, thank you very much.
Yes, thank you very much for the nice presentation. It was very interesting. I was just wondering that when you apply these techniques to mean field games, do you still need monotonicity?
Okay, so as I tried to explain at the beginning, I mean, this is essentially a talk on the decay estimates of the two semigroups, if you want. So one generated by the Fokker-Planck with zero average, of course, in the space of zero average solutions, and one generated by the adjoint operator. Then this is totally independent, of course, on the monotonicity. So to go back at the beginning, essentially, this is what I presented are estimates, which are just to answer this kind of questions. So they allow to provide a decay under certain conditions, of course. And so they are independent on the monotonicity, but when you want to use, it depends on the goal. If you now want to use that for the long time behavior, then there was a crucial step I was mentioning at the beginning that was relying on the monotonicity. And it was this type of decreasing character. But this is so somehow you have to separate. One is the stability in the mean-field game system. This is given by monotonicity. And the other is now how to use, you expect this convergence, but you need to work on the linearized or something like that. And then you want to get at estimates from this stability, and that's more or less what I discussed. I don't know if I answered your question.
Yeah, it is clear. So as long as you have something like this, if by magic you can get this kind of inequality that you have here, then your method will apply and will give you like rates.
Yes, of course you can also use this rates for other purposes. You may try to use that, for example, for uniqueness purposes. Simply by matching the two semigroups. You can try to do that, and this is also something we did a little bit with Marco Cirant in our last paper.
Thank you very much. This answers my question.
Alessio, this is Pierre. Precisely on your slide here, do you have any information on omega now, or is it just omega
on
the decay rate? How do you? I mean, how do you prove how omega does appear in your computation?
So that's a good question. Unfortunately, that's really I cannot say other than the method is nonlinear, as I said, to get this kind of estimate. Then by duality you may transport that, but the point is that this is in the doubling variable method. It's hardly seen sharpness of this kind of estimate. And so I cannot really say anything about this omega. And so the rate of convergence, the rate omega is really hidden inside the estimate I gave. Of course, if you have very, very precise models, it's possible to go through the proof, but this is maybe the point which I already tried to stress. When you go through functional inequalities, as of course, I mean, very, very strong people did, like of course, Villani popularized that a lot. Then it's clear that you may try to relate this rate to the best constants in functional inequalities and so on. It's true that to do that, they need to know the drift pretty well. So this is a different spirit in my presentation, where I don't want to know much on the drift. It can be even time dependent. It can even maybe have a bounded perturbation, which I totally don't control. So I really cannot say anything in that case on the rate omega.
Okay, thank you, Alessio. So I don't see any other question. So I suggest we resume at 11, and thank you again, Alessio.